Hello students, welcome to my YouTube channel. In this video lecture, I'm going to answer questions from sample paper number 5, the 4th edition of RK Bali navigation book. Now if you have any other edition book like the 5th one, the 6th one, the 7th one, no issues. The questions in those books are the same as the questions in this particular book. Let's start question 51, question 41. If a pilot lands at an aerodrome other than the destination aerodrome specified in the flight plan, he must ensure that the ATC unit at the destination aerodrome is informed within a certain number of minutes of his planned ETA at destination. The number of minutes is 30, 15, 45. So the correct answer is 30 minutes. So you have 30 minutes uh, to inform the ATC unit that you have actually landed at a different aerodrome, an aerodrome different from the destination aerodrome that you filed in the flight plan. Okay, so once you land at a different aerodrome, you have 30 minutes of time. Okay, within of your planned ETA. Let's say your planned ETA at destination is 2 o'clock in the afternoon. So you have 30 minutes extra to call and inform them that you have landed at some different aerodrome. If you fail to do so, they will start search and rescue operations. Right. So if a pilot lands at an aerodrome other than the destination aerodrome specified in the flight plan, okay, it should be specified in the flight plan. He must ensure that the ATC unit at the destination aerodrome, ATC unit at the destination aerodrome, not any other aerodrome, but the destination aerodrome, is informed within 30 minutes of his planned ETA at destination. The number of minutes is 30. You make a diversion from the route given in the flight plan and land at an uncontrolled airfield. Within what time after landing should you inform ATC? Now you have landed at an uncontrolled airfield. Uncontrolled airfield, that means there is no ATC tower on that airfield. So once you land on that airfield, you are going to call ATC unit, the nearest ATC unit, and you are going to inform them that you have landed at that uncontrolled airfield. And so your flight plan will get uh, uh, cancelled. Okay, or the flight plan will be completed. So within what time after landing should you inform ATC? You should inform within 30 minutes of your landing. Okay, next. The scale on a Lambert conformal conical chart is constant along a meridian of longitude, is constant along a parallel of latitude, varies slightly as a function of latitude and longitude. Now Lambert's conformal chart. So let's say this is your Lambert's conformal chart. You will have two standard parallels. Standard parallel number 1, standard parallel number 2. Okay, and then you will have a parallel of origin. Parallel of origin. Okay, now the scale of a Lambert's conformal chart is correct at standard parallel. So scale will be correct at standard parallel 1. Scale will be correct at standard parallel number 2. Beyond these two standard parallels, the scale will expand. The scale will expand. Within these two standard parallels, the scale will contract. The scale will contract. Okay. So, in other words, the scale will be correct at a particular parallel of latitude, not longitude. So, the correct answer here is constant along a parallel of latitude. Right? Next. On a direct Mercator chart, a rhumb line appears as a small circle concave. Concave means bending away to the nearer pole. A straight line, a curve convex to the nearer pole. So the correct answer is, on a Mercator chart, a rhumb line is a straight line. 45. Aircraft was over Quebec at 13:20 flying directly to Romeo. Distance between them is so and so. True airspeed is given. Outbound, going outbound, you are faced with a headwind of minus 90 knots. Uh, Coming back, you are getting a tailwind of plus 75. Endurance is 10 hours. The distance from departure to the point of safe return is how much? Okay, so let's draw the diagram. This is your departure, this is your destination. You're flying from departure to destination. Somewhere along the journey, you have point of no return or point of safe return. So aircraft will first originate from its departure location at a true airspeed of 480 knots. True airspeed 480 knots. Now when it's flying outbound, it's faced with a headwind of minus 90 knots. A headwind of minus 90 knots. So the ground speed will be equal to true airspeed minus headwind, that is 480 minus 90, that is equal to 390. Now coming homebound, the true airspeed of your aircraft is the same. True airspeed is the same 480. But now coming homebound, you are getting a push, a tailwind of plus 75. Plus 75 knots. So your ground speed will be equal to true airspeed plus tailwind. So 480 plus 75. 480 plus 75, that is 555. So ground speed homebound is 555, outbound is 390. Now let's use the formula. Distance to PNR is equal to endurance into outbound into homebound divided by outbound plus homebound. So endurance is 10 hours, outbound speed is 390, homebound speed is 555 divided by 390 plus 555. So 945 is here in the denominator. 390 into 555 into 10 is 2164,500. So that divided by 945 is 2290 nautical miles. So the correct answer here will be the distance from departure to the point of safe return is 2290. You can select any option which is closest to this value. An island is observed to be 15 degree to your left side, to your left. That means 15 degree to the left of your heading. The aircraft heading is 120. Variation is 17 degree west. What is the bearing from aircraft to the island? So you want to find out true bearing from aircraft to the island, meaning QUJ. QUJ. So let's say this is your radar screen, airborne weather radar screen. Okay. This is the heading of your aircraft, straight line. Now that heading is 120 magnetic. In terms of true, it will be equal to, now variation is west. Variation west, magnetic will be best. So true will be less than magnetic. 120 minus 17, 103. 103 true. Now this island is 15 degree to the left hand side. So 15 degree to the left means somewhere here. Okay. So 15 degree to the left hand side. So relative bearing is, I'm going to write it here. Relative bearing is minus 15. Right? Next, use the formula QDM. Magnetic bearing to the station is magnetic heading plus relative bearing. So magnetic heading is 120. Relative bearing is minus 15. So 120 minus 15 is equal to 105. That is QDM for magnetic bearing to the station. True bearing or QUJ to the station that they have asked us to find will be equal to QDM minus variation. So 105 minus variation, 17 degree west. So 105 minus 17 is 088. So QUJ to the station is 088. 8. Option Charlie. Next. During a climb after takeoff from a contaminated runway, if the total pressure probe of the airspeed indicator is locked, the pilot or the indicated airspeed, what will happen to indicated airspeed? So now your airspeed indicator, let's say this is your airspeed indicator, right? Now dependent on, it is dependent on two things. A pitot tube, correct? A pitot tube. So let's say this is your pitot tube and a static port, a static port, okay, and a static port. Now this pitot tube will transmit pitot pressure into the aneroid capsules, and static port will transmit static pressure around the in the remaining instrument, that is around this pitot, around this aneroid capsule. It will transmit static pressure. Okay, so static pressure will be filled in this instrument case, and we will have dynamic correction, pitot pressure inside the aneroid capsule. So now if pitot tube gets blocked completely, this pitot tube gets blocked completely, what will happen? There will be no input of pitot pressure in the pitot tube, pitot pressure in the airspeed indicator. The only input that it will get or it will receive will be the input from static port, and static port will transmit static pressure only. That means once your aircraft has taken off from the runway and is climbing and starts climbing, so it will respond to changes in static pressure, changes in static pressure only. And what other instrument reacts only to changes in static pressure? VSI, altimeter, right? So it will respond to changes in static pressure only because it is not receiving pitot pressure. Now what happens when you climb to higher altitudes? The static pressure goes on decreasing in values. Okay, in value. So that means as static pressure goes on decreasing in value, the registration of that static pressure will also start decreasing. If the registration of that static pressure by the ASI starts decreasing, the value shown by the airspeed indicator will also start decreasing. So the final output that you will get is that you will slowly and slowly get an airspeed indication of lower and lower value. So correct answer is uh, the takeoff. So okay. So airspeed indicator will respond to changes in static pressure only. Now when you go to higher and higher altitude, static pressure goes on decreasing. This decrease in static pressure will have an impact on this aneroid capsule. This aneroid capsule will start expanding. It will start expanding. Its size will start growing. Just like the aneroid capsule in an altimeter. What happens in an altimeter? When static pressure starts decreasing, the aneroid capsule start expanding, right? And this expansion in the size is transmitted to via mechanical linkages, and finally we get an output, an information of increase in altitude. Similarly, in this ASI instrument, the decrease in static pressure as aircraft climbs to higher and higher altitudes will be registered by this aneroid capsule. It will expand, and this expansion will be transmitted via linkages to the airspeed indicator needle, and that needle will show an increase in airspeed value. Just like an altimeter. Altimeter shows an increase in altitude. Similarly, airspeed indicator will show an increase in airspeed value, even if you are not increasing your airspeed. Okay, so that is an error. So what will happen? It will increase steadily. Okay, because you are going to climb in a steady manner to higher and higher altitudes, not just zoom away to higher altitudes. So it will increase steadily and not abruptly or suddenly towards maximum speed, which is Vn. So very important. Next, with pitot tube blocked due to ice buildup, airspeed indicator will indicate in descent what? Now this is the opposite of flight. It's similar to the previous question. The concept is the same. The wording has changed. Now in this previous question, we checked climbing, a climbing plane. So in a climbing attitude, the airspeed will increase steadily because static pressure decreases in value as you go to higher altitudes. This decrease in static pressure will expand the aneroid capsule, and this expansion will be treated as increase in airspeed. Now, when you descend to lower altitudes with a pitot tube block, that means no pitot pressure is getting in the inside of the aneroid capsule. The only thing that we are receiving will be the static pressure. So this aneroid capsule will only respond to changes in static pressure. So as you descend to lower altitudes, static pressure goes on increasing. This increase in static pressure will have an impact on aneroid capsule. What happens when static pressure increases? The aneroid capsules will shrink. Okay, the aneroid capsules will get compressed. So this increase in static pressure will compress this aneroid capsule. The size of that aneroid capsule will start decreasing, will start shrinking, and this motion is transmitted to the airspeed indicator needle, and the final output that we get to see is a decrease in airspeed value. Just like an altimeter, when you descend to lower altitudes, the aneroid capsules shrink and the altimeter shows a decrease in altitude, right? A decrease in vertical distance, altitude, height, pressure, altitude, whatever. So similarly, your airspeed indicator will slowly start showing a decrease in its values. So the correct answer is increasing speed, fluctuating speed, decreasing speed. So option Charlie. It's very important to understand that pitot tube is completely blocked. So the only inputs that are going in the airspeed indicator is the static pressure. So it will work or it will get manipulated by static pressure alone. Once you understand this, you will be able to select the right answer. 49. The density altitude. Now what is density altitude? Density altitude depends on the density of your atmosphere. Now this density of atmosphere is controlled by three things: temperature, okay, next pressure, the third humidity. Now increase in temperature lowers or decreases the density of air. So if density of atmosphere decreases, that means the working efficiency of your aircraft will decrease. And as a matter of fact, as a result, the density altitude will increase. What is density altitude? Density altitude is nothing but pressure altitude plus 118 into ISA deviation. So now let's say you are flying at you have parked your aircraft at mean sea level. Okay, you have parked your aircraft at mean sea level. ISA conditions exist. Now in the presence of ISA conditions, the pressure altitude of your aircraft, which is nothing but mean sea level, will be equal to the density altitude. Okay, but let's say now you are parked your aircraft, parked your aircraft on mean sea level. Okay, and the conditions outside are warmer than ISA, hotter than ISA. So warmer temperatures will decrease the density of atmosphere. This decrease in density of atmosphere will have an impact or influence on your engines, on your aircraft speeds, etc. So what will happen? Even though your aircraft is parked at mean sea level, the behavior that it will the behavior that it shows, or the manner in which it operates or works, its engines work, will be according to an altitude where the density is found at mean sea level. So let's say you are at mean sea level, and the density at mean sea level is not 1.225 kilogram per meter cube. Okay, it's less than that. So now this lesser density is seen at higher and higher altitudes. When you go to higher altitudes, the density of air starts decreasing. But at mean sea level, if the density is less, that means you are physically located on mean sea level, but the behavior that your aircraft will show or the manner in which it will work will be according to the manner this aircraft will work at some other higher altitude. For example, 5,000 feet, 10,000 feet depends. If the density at mean sea level is equal to density that is normally found at 5,000 feet, 10,000 feet in ISA conditions, then your aircraft will behave accordingly, will behave according to the density at 5,000 feet. So your performance parameters will decrease. Okay, the performance of your aircraft will not be the best. It will suffer. So this is called density altitude. So just because we are located at mean sea level, that doesn't mean your aircraft will behave or will give maximum performance. You have to check your density altitude, especially for takeoff at the time of takeoff and landing, to check your takeoff distances, landing distances, your speeds, etc. Okay, so density altitude is therefore dependent on pressure altitude and ISA deviation. ISA deviation means ISA temperature deviation. Warmer than ISA temperatures decrease density of air, which increase the density altitude. Colder than ISA temperatures, good. They are good for performance, so they increase the density of air. Increase the in density of air means lowering or decrease in density altitude. Similarly, pressure. Now, when atmospheric pressure increases, the density of air increases, so density altitude will decrease. If atmospheric pressure decreases, density of air will also decrease, and your density altitude will increase. Humidity. Now, when air is humid, the density of air decreases. Okay, it lowers down, and therefore density altitude will increase. If air is dry, density of air will be very good. It will be high, and density altitude will be low. So these are the three parameters or three factors that control the density of atmosphere at some time. You can watch detailed lectures on the theory of density altitude on my channel. I have made two theoretical lectures on density altitude and already uploaded them to my channel. You can find them in one playlist. I think RK Bali GenNav or Oxford GenNav playlist. You can find it there. I have also solved density altitude based questions, pressure altitude based questions from RK Bali DR Elements of Temperature Pressure chapter, and I have also solved questions from Oxford Altimetry chapter. So density, altitude, pressure, altitude questions are also feature in that particular chapter. So you can watch video lectures of both these chapters. You can find them in the playlist. So let's check the answer. The density altitude is the altitude of the standard atmosphere on which the density is equal to the actual density of atmosphere. It's the temperature altitude corrected for difference between real and standard temperature. It's pressure altitude corrected for relative density. So correct answer is uh, option A. The altitude of the standard atmosphere on which density is equal to the prevailing density. What will happen to altimeter reading in a right side slip if aircraft has a static vent on both sides but the left one is blocked? So let's say this is your aircraft. Okay, this is the fuselage of your aircraft, and it's flying in the north direction. You have two static ports on both sides of your aircraft, left side and right side. Now these two static ports are provided so that we get an accurate registration of static pressure irrespective of the attitude of your flight, whether you're turning left, you're turning right, okay, whatever that is. So these two static ports will compensate for each other's errors, drawbacks, shortcomings, and as a result, we will keep getting the right registration of static pressure in our pressure instruments and hence accurate readings. Now let's say your aircraft has entered in a right side slip. It's entered in a right side slip. So it is going on the right, it's drifting to the right hand side, okay, like this. Now what will happen? The left static port is blocked. The left static port is blocked, meaning the left static port is unavailable to us. we are only going to use one static port, the right static port on the right side of the fuselage. Now this right static port will be directly exposed to the oncoming relative airflow, whereas the left static port will not be exposed to the incoming airflow which is coming from the front, because since its aircraft is in a right side slip position, the left static port will get hidden or get masked from the relative airflow. And irrespective of that, the left static port is blocked. So whether you are in a side slip or not in a side slip, the left static port won't be able to register any static pressure around it. So now we are dependent on only one right static port. Now since this right side of the fuselage is exposed to the relative airflow, the pressure felt the pressure felt by the right static port will be equal to static pressure, which is already there in the atmosphere, plus the impact pressure created by or generated by this relative airflow. Okay, that is called dynamic pressure. That is called dynamic pressure. Okay, so as a result, the pressure registered by this right static port will be much more than the atmospheric pressure, which is only static pressure, but it is experiencing or it is registering an extra dynamic pressure. So much more than expected pressure. Now, what happens in ISA atmosphere when you climb to higher altitudes? Atmospheric pressure goes on decreasing. When you descend to lower altitudes, atmospheric pressure goes on increasing. Right now, this higher pressure on the right hand side, registered by the static port, the right static port, will be interpreted as a lower altitude indication. So low altitudes means high pressure, high altitudes means low atmospheric pressure. So that is how the interpretation happens. So this right static port will falsely register a higher static pressure, and this higher static pressure will be interpreted or translated into a corresponding lower altitude indication. So you may be in a right side slip at a level altitude, let's say 5,000 feet. You are not descending, you are not climbing, but the altimeter will show an indication which is less than the altitude you are actually flying. So if you are flying at 5,000, a level flight at 5,000, that means you will be shown an altitude less than 5,000, let's say 4,000 feet. Okay, so any altitude less than that. Why? Because high pressure exists on the right side of the fuselage. So the correct answer is, what will happen to altimeter reading? The altimeter reading will underread. It will underread. Next. So that's it. So this concludes a lecture. I hope you have understood all the 10 questions that I have answered in this video lecture. Practice these questions multiple times. Read the theoretical chapters associated with them. Watch other video lectures that I've already uploaded to my YouTube channel relevant to this particular questions. The more you practice questions, the more proficient you become in them. You become more confident. Your time management improves. So with this, I wish you all the best. I urge you all to share this channel, this particular video lecture with your friends. Subscribe if you haven't yet, and hit the like button if you have liked this video lecture. In my next video lecture, I will start solving the next remaining sums from this sample paper and remaining sample papers. So don't miss that.